our goal was to find a low-power embedded computer that had enough processing power to interpret the data from the Kinect and then output it using a communications protocol to any microcontroller or other device that would want to talk and get the Kinect data. So we found the this Protec Systems embedded computer that runs on 12 watts of power and has 1.86 gigahertz of processing speed. So it has enough to run and interpret the data in real time and output it to these processors. So we set up a protocol that lets you define which joints you want to use, and it can do up to 24 joints: head, neck, collarbone, shoulders, torso, hip, elbows, wrists, hands, knees, and feet.
So is the recognition of the joints actually done inside the Kinect box?
No, the Kinect gives depth data. That's the distance to.
Right. Okay.
I think it's like the inverse. It's inversely proportional to the distance.
Okay.
From. Then we have middleware libraries that we found that are open source that do the actual conversion to the skeleton joints. And then that data is given in millimeters as X, Y, and Z coordinates from the center of that Kinect.
Okay.
And then our demo program is we have 2 servo motors set up. This servo motor will follow the closest right hand to the Kinect. This one will follow the second closest. And we've kind of got lines taped on the floor. And that's the minimum distance you have to be away to be in frame.
I see. So it's tracking right. Okay, it's working pretty well. Cool.
And if there were a second person, it would that were farther behind you, it would track with the other one.
So what did you program it in?
C++ for the code that does the communications protocol. C for the Mega32 demo code.
And then did you implement? So you have. Okay, so these are all at Mega 32s speaking the protocol back to here.
Only the first one is actually doing the communication. The other 2, except the third one, isn't working right now. Just listen in the background.
Okay.
So yes, this one is the one that actually does the requesting.
But it says I only want the right hand data, which is it sends a 1 byte message.
Yeah.
It sends a 1 byte message that has bits on or off for each individual joint. That gets interpreted by the code on this side, which sends back how many users there's going to be, and then the joints for each individual user.
Okay. And then the hardware that you're running on, how much would it cost if someone wanted to buy one of these so they could use your system?
That's the kind of downer part of this. Is originally we were doing this with the Beagle board because the middleware library said they were optimized for the ARM architecture. It turns out they were not. And there will be they're coming out with version 2.0 this summer in July, which supposedly should support ARM.
Okay.
So we started out working towards that, and then at the last minute we kind of had to scramble and find something else. So this is a full, I think it's a 32-bit architecture, and it costs $450.
So you've proven the concept, but now you need to move it down to that
to a more
hardware where the
affordable
library can.
The libraries that we're using is what actually does the skeletal tracking, and that is a whole senior design project in itself.
Oh yeah.
We looked at that and doing that, and they're like, nope, we don't have to.
It's probably open source, but that, like you say, that would have been a separate project.
Yeah,
So
that's a new project
you wouldn't have been able to
itself,
do your project. Okay.
Exactly.
Oh, cool. Thanks for the demo.
Yep. And now you're out of range. So I guess when you got